Yo, alright, what's up everyone? Welcome to week 67 of Chill Kernel Hacking for Fun. Thanks for joining. We're getting back at it. Let me take a moment just to get set up, but today we are diving back into the interesting world of computer networking. I will do my typical test messages in the chat. Nice. Yeah, so we are diving back into networking today, and I have something to explain. So last time in last week's stream, I wasn't able to really fully debug things, if I recall correctly. I was going on this adventure to try to get data properly sent into the OS over the network, and I was struggling a lot with QEMU. And we figured out some key problems with my setup. I was using some of the wrong command line arguments for QEMU. But there were also a bunch of other problems that I had. I spent a little bit of time debugging it off stream, and I believe I got things working. So we're gonna get back into this, and I'll explain anything that I learned. All right, so we got tweet sent out. Let me just double check that. Yes, sir. All right. Close a few tabs. Yeah, so let's see. We have our Miro area set up for today. Why is that? This resolution seems like really awful for some reason for some of these screenshots. I wonder what happened there. Let me try refreshing. Okay, it's workable. Today is the 11th of May. It's week 67. All right, anything else to do? All right, now let's dive into it. So, okay. This is like this big temp commit. Get my fork client out. This is like this big commit, which has a bunch of stuff. I think I will need to clean this up a little bit. Okay, let's try this out. What's over here? Okay. So we're going to run the kernel with this test input program. And this is usually a sign. Okay, the kernel did not start, but that is usually a sign that something was off in the init process here. I think the file system. Yes, okay. If I don't know, if this file system thing is like not active, then it like hangs there. Anyway, so this is kind of the state we had things. We have an operating system, it boots up, and on initialization, it runs this application. Has to input, and the application sends an ARP announcement packet. And we receive an ARP response. And that's what we are seeing right here. And so the OS is listening for data coming back in over the network, receives it, and then it just hex dumps it out. And now it sits there in a loop waiting for more data. And that's what we see here in this loop. It's just waiting for data from the network. And if it receives it, it hex dumps it. And what I was trying to do, ideally, we would be able to actually send data from my host machine into the VM. And it looks like that is working. I think I need a small timeout here for the netcat command. I believe netcat waits to receive data back from the server or something. But so what we can see is that we're able to send some data over the network as UDP packets. That's what the -u does to the VM. To the VM running the OS, and the OS receives the data and hex dumps it. So things are kind of working. Right. And what did it take to get this to work? So just to start off, I'm going to okay, that was weird. It seems like the stream stopped briefly. Okay, that's annoying. The stream disconnected briefly. That's kind of annoying. But we should be back now. We'll just double check. Right. Okay. Some technical issues today. These are these grading scripts that I'm trying to get working. This is the make file change. This is some input file. And this is just a bit of debugging stuff. Yeah, this is all just a bit of stuff I was using to debug why things weren't working. And I'm looking for one particular change I made, which is right here. So I had this, I had this really serious problem with my network driver. I just had a copy paste error where I had this kind of random struct member in my struct for the receive descriptor, and that was really serious because it caused the structure to mismatch with the structure the hardware was expecting, and that's why my receives weren't working. So that's what, How's the stream? Is the stream? A lot of technical issues with the stream today. Okay, so here, here is a very important change. So here is where I am adjusting my QEMU command line arguments to no longer add separate NICs for each port forward from the host, but just do it all with one NIC. That's super important. So, you know what, I'm just going to So just to start off, there's a lot of stuff I don't need anymore because I got this all working. Okay, I'm just going to start from basics. I'm just going to simply kind of stage this thing. Make file fix QEMU args. Don't add separate NICs. Previously, we were actually adding separate NIC devices for each port forward. Okay, nice. Hello to everyone joining the chat. Okay, what would be next? I think this stuff is no longer needed. This is no longer needed. This is no longer needed. This was a small change because this causes some extra output to come out of QEMU for kind of debug logging, and I think it was messing with the grading scripts, so I disabled it for that reason. This is kind of during development, I have this kind of fake sleep in there to kind of slow things down. Maybe I will just keep that in there for the moment. Okay, then this is a temporary change to reduce the number of RX descriptors. I did that while I was debugging things. I think I might also just leave this in here for now, and then I think I don't necessarily need these anymore, but I think I might just stash them just in case they come in handy. So this receive. It's like, what is this doing? This is commenting out a comment that was, you know, I'm just gonna get rid of this stuff. So this head thing, is this used anywhere? I'm not seeing a use of this. Okay. Slowly kind of getting somewhere here. And then the whole goal was to pass these tests. And let's take a look at the tests now. Or rather, let's actually just quickly check in back on the lab. So the lab's saying you should pass the test input tests of make grade. And what it's talking about are these test input right here. And so I believe I got things working now because I got all this port forwarding stuff. So I was able to show that we can netcat data into the VM successfully and have it be received. So we can run the testing script now and see what happens. And we passed the tests. And just out of curiosity, what does Wireshark say? So in the Wireshark, we can see the initial ARP request and reply, and then we can see it's just basically a bunch of UDP packets with this like packet string in there. And these are coming from this function. So the way the test works is that it spawns a thread, and in the thread it sends UDP packets through this port forwarding thing into the VM, and this is where it constructs these strings that it passes in. Yeah, and then it runs the VM, which is going to try to receive all that data. At the very end, it's going to do some validation on the PCAP file at the end. So it's going to parse the PCAP file and it's confirming a few things in the PCAP file. It's confirming that there's the ARP request response is there, and then it's doing some checking on this packet string thing. What's up, Bacon? Nice to see you. So anyway, so we're officially passing those tests, which is a good thing. I think I'm going to actually revert this change and bring it back to 128 descriptors. Not quite sure about this one. This one enables broadcast, something with broadcast on the receive side of the NIC. I don't think we actually need that, but I had it in there. I've disabled it and things are working, but I'm not sure if it's bad to put it back in actually. So, yeah. I'm gonna go and just delete this hunk. So now we can try to move on and run this test. And this is interesting because I think it wasn't passing because it was timing out. Oh, okay, that didn't time out. That just straight up failed. Interesting. So the only difference between these two tests is that the first one sends 5 packets and the second one sends 100 packets. And it seems like something went wrong there. So I don't know if it's a problem with my code actually, or if it's a problem with the test infrastructure, because the test scripts do a lot of parsing of stuff. Like they parse QEMU's output, for example. And I'm suspecting that could be a little bit fragile, and maybe the tests are failing because I have some differences in my QEMU output, maybe because I have print statements or something, and it's maybe failing that. It also does a bunch of parsing of the PCAP, which should be a bit more resilient. But what I'm just going to do is I'm going to slowly work my way up into higher numbers, or maybe I'll just bisect what the problem is. I'm just going to start off with a nice easy 25. Let's see if we can do 25 packets. So that didn't even work. So, but 5 definitely worked, right? That did work. Yeah. What about 15 packets? So that didn't even work. Let's just input 5. And QEMU output saved to this JOS thing. JOS.out test input 5. So there's clearly output here. Let's look at the PCAP. Also, hello to everyone joining the stream. Welcome. So if look over here, so we're definitely getting the data. It starts at 0. Oops. Starts at 0. Does it show me how many? Selected 15 packets. So I am kind of mistrustful of the test script because it really seems like all the packets are here. All 15 of them. But for some reason, this test is failing, which is kind of annoying. Just out of curiosity, what if we crank it up even higher? Let's do 50. It seems like that passed. That is kind of unexpected. So that failed. Let's open this up. Also, Wireshark. The last one's packet 49. So, so I guess what does this Wireshark thing even say? This is just this is capturing the data that went on the network, but just because, oh, I see. But just because this data went on the network doesn't mean it was received properly by the OS. So presumably that's what this thing is trying to test. And okay, I see. So I'd love to not really spend that much time debugging this if possible. So maybe let's go back to our known working state and just get it. It seemed to be reliably working at 5 packets. Just make a note of that. 5 packets reliably works. Well, apparently, never mind. Because that just failed. So actually, no, there's non-determinism. So just to check out again. So here's the simple 5 packet PCAP. So definitely those packets were sent on the network. And here is the data that we see from QEMU. 1, 2, 3, 4, 5. So I don't exactly know what's in this. This looks like the string, but from a first glance, it would seem like 5 packets were received. And we can even take Wireshark over here on the right and do a very quick comparison to see if this looks about right. So this is the first one that would correspond to this one. And it seems to be matching up. We see this, so the particular byte that's going to differ is like over this 2030 thing. But actually, this is kind of interesting. So this looks kind of wrong, actually. The first one should have a 30. It's 20, 30, 30, 30, 0, 0, 0. And then that 4th byte of the last row changes. And we kind of have that, except weirdly, this thing says 31 instead of 30. So that's worth a screenshot. Hey, Miho. Nice to see you again, and thank you for the debugging help. So we were saying first packet seems ignored, second it seems duplicated. Let me just check that again. So first packet, right? As you notice, it is being ignored, and then so the second one with this one is being duplicated somehow. It's taking the place of both the first and the second. So that is interesting. Be ignored. Second packet being duplicated and taking the place of the first and second. All right. Let's see if we can understand why. That is actually kind of a fascinating problem. But what is also fascinating is why why is it non-deterministic? Copy. I'm just gonna call this fail 5 1. Because it doesn't fail every time. So that's a little bit spooky. If we run it again, it's going to pass. Yeah, so it just passed. So it is non-deterministically failing, which is always scary. It's passing. It seems to pass most of the time for 5, but it seems like if we crank it up to like 10 or something, even just a little bit higher than 5, we can make it fail. Unless we can't. So that also passed. That also is passing. That is also passing. Okay, I was very much expecting it to fail. 10 just passed 5 times in a row or so. If all packets are logged, there is a missing one from the Wireshark ARP setup. Oh, do you mean here? Let's just double check. So I believe, so this is the first packet we receive, and I think that, that's this one. I think that should be this one. Does that seem right? 54, that looks right to me. So I think the ARP response is actually there, if that is what you're saying, although maybe I misunderstood. Let's crank it up to 20 and see how it responds. Now I'm fully expecting it to fail. Oops. It's somehow still succeeding. What is going on? This is whack. Okay. Did this? Oops. Okay. I just tried to run Wireshark, but it didn't create anything because it is passing the tests. One more time. Very odd. 25? Okay, we got our failure. I'm just going to screenshot this failure message. Okay, Wireshark session again. So this is 0, 20, oops, dang. This should be 24. Okay, so this is what the theoretical data should be. Let's take a look at, called fail 25, 1. Less fail 25, 1. And do we see the same symptom? We don't, actually. It's interesting. And maybe even this. Yeah. So at some point there, last one was at index 1819. Let's take a look at that. A little bit annoying to figure out which one. So, right, so what is the easiest way to figure out? It's hex 30, right? Hex 30 plus 18 hex is hex 42. Okay. So that is going to be did I do something stupid? I was kind of expecting okay, maybe that was a bit too quick. So oh wait, no, it's because it's like okay. The easiest way is probably just to look right here. So it's this 3138 thing. That's the thing to look for. And so here we go. Here we can see it. The 39 is duplicated twice. We can see that right here. If we compare against Wireshark. It should just be nice, simple, 31, 36, 37, 38, 39, back to 30. So yeah, so Michal, I believe you're right. Some packets are really duped and skipped. In a non-deterministic way. Same issue as above. Packets, one packet being duplicated, the next one, one packet being skipped, the next packet being duplicated. In a non-deterministic way. Okay, so this is interesting. Wow, what could be causing non-determinism here? I'm not sure, but what I do know is that it's a good time to take a quick break to stand up and stretch. I will be right back. Smells like a race or an out of order. Read, write, lock order. Interesting. Out of order, read, write, lock order. I'm just thinking about how to go about debugging this. So first step would just be, we want to be able to reproduce this deterministically. I still think that if we ramp up the number high enough, for example, to 50, we can reproduce it every time. So that's a very basic start to this. So that failed. Good. What's up, Ragil? Even though I don't understand any of this, I want to hang out here while I'm coding web projects. Absolutely. Please do. You're very welcome to do so. Yeah. Sorry if it's a little bit deep right now, but we're in kind of this like really deep bug with my operating system, with networking. And it's actually pretty interesting. And yeah, but yeah, you are absolutely welcome to hang out. Okay, so this is failing every single time. This was on packet 2 out of 50, I believe. Was that also on packet 2 out of 50? Missing packet 1. It actually always says 2 out of 50. No, I'm misreading that. 1 out of 50. And that one actually passed. That one actually passed. Yeah. 13 out of 50. Okay, so we can very clearly just see this. It shows you we got an unexpected packet. We were expecting the 12. We got the 13 instead. So what I would like to do is reproduce this outside of the testing environment. I would like to just run my OS, and then use my send.py script, which I wrote as a very light simulation of what the actual testing script is doing. And I would like to be able to reproduce this there, outside of the testing infrastructure. Because then if I can do that, maybe I can add some extra logging and stuff. Making your own kernel for your own OS. Sort of, kind of. What I'm actually doing is I'm following this coursework. It's like free coursework on the internet. But at this point, I've been working on this for about a year, and I've customized it a decent amount for myself. So it feels a little bit like partially owned by me. But I also didn't write a lot of the code. But I wrote all the code relevant here. I wrote the buggy code, I'm pretty confident. So this bug is completely my fault. So let's start with that idea I had. I just want to be able to kind of reproduce this duplication of data, and let's just try. So just to try out doing that, what I'm going to do, I'm just going to run the OS in like normal mode. And now it is sitting there waiting for packets. And we have my script, handy little script here, and it's doing pretty much the exact same thing. It's sending 5 things. So if I go ahead and do Python 3 send.py, we can see that it kind of worked. It sent a bunch of stuff into the OS, which was received here. Yeah, so that's like a very small start. then what I can do is I can just make this like a high number. The problem is though, it's kind of annoying just to have this output here in my terminal. It would be nicer to have it in a file. Maybe at least just for analyzing it. I think it is randomized depending if the OS received 2+ frames in the same interrupted. Should be reproduced by bursting packets as fast as possible. Yeah, so, well, the thing is there's no interrupts actually happening here. Like the way it's working is just polling. Actually, I have kind of a weird idea. I actually wonder if my weird sleep loop is interfering with, I'm just for, yeah, just to be really sure, I'm going to disable that. Let's try this again. I expect it to still fail. Okay, still failed on 1 out of 50. So really early on. At least that's kind of a good sign. But that one actually passed. Okay, so that did not help anything, but it just reduces the variables in the equation. I disabled my tracing stuff here. Okay, let's go back to my original idea. So we have the normal OS running, and then we're going to just send 50 packets. And it kind of did that. So now the problem is that it's very difficult to just like see if there was a problem, but we can see it here actually. 36 got duplicated. So okay. So nice. So now we're able to reproduce it outside of can repro it outside the testing and script. The 36 here is duplicated. Which is interesting. Instead of reducing the loop count, increasing might help reproduce it reliably. I think I probably did not optimize the loop. Interesting. So okay, I understand what you're saying. So maybe we actually want the loop, but like kind of a big loop might even be better. It makes the test run slower, but it's worth a shot. Let's try it. So I have my loop back. It's kind of large. This is a loop. The purpose of this loop is to slow down the process that's asking for data and basically spamming the driver. We have this user space program that's just going in a loop and just asking and just doing a system call that asks for data from the driver like super often. And it really spams the driver, and maybe that's a bad thing. And so this loop kind of slows things down. I don't think it's getting optimized. I was able to use this to observe it getting slowed down in the past. And so maybe the idea here is to make it more deterministic actually, which is always a good thing. So that just passed. Okay, that failed at 33. So it's still kind of non-deterministic, even with that crazy, or even with the fake sleep loop. But it seems to be passing quite a bit, actually. I wonder if I raise it high enough, if that will actually just fully solve the problem. Nope. Failed on 40 out of 50. Yeah, prerequisite to build a kernel. Yeah. Yeah, definitely. I would agree with Miko. Like, in general, knowing the architecture you're building for is pretty important. I think, but I mean, on a more general level, I think you need to be pretty comfortable with like C programming and base understanding of assembly. Yeah, I mean, there's just so much with operating systems. A strong understanding of like the concepts around what an operating system is and is trying to do, like virtualized resources and like what virtual memory is. You can learn a lot about this stuff without actually building a kernel, just from resources and stuff. And then when you want to go really deeper into it, you can build a kernel to like really flesh out your understanding. Okay, that did not help. This thing is still failing. What I actually want to do is just, I want to make it fail every single time. I'm just going to make this 100. I don't think I've ever seen it pass with 100. It sort of seemed like making the, oh wow, it just did actually. It sort of seemed like making that loop a bit longer stabilizes it somehow. This is funny. It's passing every single time. I just said I've never seen it pass with 100. Now it's passing every single time. Right? Just to be really sure. We're passing in 100 to it. And we also have this really large loop iteration, which really like slows down the system. Okay, it just failed. Okay, at 12 out of 100. Okay, so big loop maybe seemed to stabilize it, but it still fails sometimes. But 100 passed quite a few times. So I'm going to go back to my original idea. I'm going to change this to 100. Yeah, I mean, we kind of already did all of this, but 100 is kind of annoying actually because there's so much output. But the good news is that the structure of the output doesn't really matter so much anymore. And then, okay, the hard part is that it's kind of hard to identify where the problem is. So it'll be useful to have some kind of post-processing script. I mean, really, I just want to be saving stuff to an output file, and yeah, I actually disabled this. Or did I? We used to have this thing that adds this -d QEMU log. I'm going to add that back now, actually. The reason I removed that was because I think it was actually suppressing the trace messages. These trace messages would go into the log file and I wasn't seeing them. But now I actually do want I'm just going to call it QEMUx.log just to distinguish it with a capital D, right? So now we should get a log file, maybe. QEMUx? Does that exist? Fuck. It is empty. What's up, Motion God? Hey, I'm new to the channel. This is impressive. How long have you been in the field? So I've just been doing this as a hobby, actually. I mean, I've been doing this as this kernel operating system stuff as a hobby for about a bit over a year at this point. Maybe like 14 months or something like that. But I've been working as a software engineer for about 10 years. Not really doing operating systems stuff though. Yeah. Also, quick shout out to the people on Twitch right now. I'm multi-streaming to Twitch as an experiment. So yeah, shout out to the Twitch viewers. Okay, so we are having some roadblocks here. This QEMU log file is empty. I am going to ask ChatGPT. How to capture QEMU's serial console output to a file. This dash serial option. That sounds exactly like what I want. Do I not have that already? I have this monstd.io. Maybe you can T the QEMU output instead. Right. What does T do? I forget what T does, right? T takes something and then also pipes it to a file, right? Test T. What's up, Krishna? Hello. Also, Brian, I need help on HTML programming. Yeah, sorry, dude. I don't even know HTML really. Okay. So good idea, Miho. So we just ran stuff, injected all our data. We closed down the OS, and does test T? Yes. So great idea. It's all there. So that's at least a start. And then we can just do some simple stuff. Like I'm just gonna grep for input 30. And I don't know, that like sort of filters out a lot of the noise. It makes it at least a little bit easier to detect when the duplication happens. And we could even get this really optimized. I wonder, like I could do my QEMU command and then I could do my ag. Ag input 30 test T. That runs this thing. We spam in all the data. I close this, then it prints out the grep thing. It's not perfect. But we can, okay, it's not that bad. Like we can visually find the duplication. What's up, Yash? Thanks for the sub, appreciate that. Yes, for anyone joining the stream, we're working on this network driver bug again this week, but I have confidence. So at least we can see. The problem is that there's the 36 here. There should be a 35 here. So the driver is, it's like missing the 35 and somehow doing something weird and replaying the 36. But that functionality, that's like, that's always happening. Even though it's a little bit deterministic, that this very particular functionality of one packet being dropped, the next packet being duplicated is what's happening every time. Cool, so here's what we can do now. What I want to do now is really, well, we should probably look at the driver and audit it a little bit just to see if there's anything obvious that would stand out. But in addition, what I want to do is just like hex dump some stuff, and that was actually that was part of the hunk that I like deleted earlier, I think, unfortunately. So I just want to add, a hex dump right at the point where we just like have the data. And how do we, yeah, it's basically just this hex dump. I'm just going to surround this with some backticks. So here is where we're really just printing out the data in the buffer that the NIC gave us. So this should really have all the right data. I'm also just kind of thinking about this. I wonder if the number of descriptors actually influences this. For example, if I'm using 128 descriptors, if I really make that way lower, I'm curious if that affects this. But the interesting thing about 128 descriptors is it's actually even more than we're even using right now. We're not even hitting, with 128 descriptors in the queue, we're not even hitting the wraparound point of the queue because we're only sending like we're only receiving like 101 packets. All right, time for a 20-second break. Be right back. Stand up and stretch. Okay, actually, so I'm actually thinking it's actually better to have a higher number here. At least that reduces the possibility of errors, because with a higher number here, we don't even reach this wraparound point, and there's a potential for the wraparound point to cause problems. So I'm just going to leave that as is for the moment. Okay. So back to our thing. Also, what's up? Unidul Yarif, any point with Rust? Not at the moment. I don't know Rust. So I'm trying to keep things a bit simpler for myself. And rather than having to learn two things at once with the OS stuff and Rust, I'm just trying to learn one. But I think Rust is cool. Maybe someday. What's up, Motion God? Oh yeah, so coding for the depth of understanding came after years. It's getting hands-on whatever project to learn. I mean, definitely years. I mean, yeah, I've been programming for like 10 years. I mean, more than that at this point, and it's just a gradual building up of knowledge. But projects are super good. Definitely work on whatever projects you can, as many projects as you can. Diverse projects in different areas of technology. Work with people that know what they're doing. Yeah. So I have added my humble little hex dump here, and let's just kind of see what happens. I'm going to keep this command line here. All right, so now we get two hex dumps. We get the one hex dump, which is like straight from the driver. And then we get this other hex dump like a little bit later, which is from user space receiving things. And theoretically, they should be the same. But in practice, maybe not. Okay, so that just finished. I'll quit. And then now let's do our kind of like bad scan. So it's again at the 35. Now let's take a look at test T. So we know that 35 was the one with the problem. Okay, dang, this is like kind of confusing actually, because the output is getting interleaved. But we can see it here basically. So we see a 33 and then a 35. So this is bad. That should be a 34. Then we would expect oh wait, no, okay. So here are the two duplicates. It's 35 here and here. Unfortunately, with the interleaving of the output, it makes it kind of hard to see what's actually happening here. And also the hex dump is like formatted differently. But even though it's kind of hard to recheck it out, we're looking for this kind of 20, 30, 30, 35 thing. 20, 30, 30, 35. And look at here, 20, 30, 30, 34. Yeah. So the data entered, it was there. This is proof that the 34 did exist, like the NIC sent it, and then something happened and messed it up on the way to user space. So this is a good sign. At least we are able to confirm the existence of the 34. Added a hex dump to the raw driver call. We observe that the 34 was actually present. then it must have been dropped later. And the 35 is somehow duplicated. So these are just my debugging notes for this situation. We can see the 34 is right there. Okay, that's good news. That's interesting. So maybe it's time to just look at the code. So this is the driver function. As I said before, our user space program is like spamming the driver. The user space program, test input, well, sorry, no, it's just input. Close some of these other tabs. Currently it's kind of regulated by this loop, but it just does this big loop where it does a sys network receive system call. And the sys network receive system call is really simple. It doesn't really do anything. It just calls this function in the driver, E1000 receive, and that's this thing we were looking at. So that's just a bit to orient you in terms of what's going on. So we have this user space program that's just in a loop doing this like very simple system call, which is just calling it into the driver. And it's calling this function a lot. And the job of this function is to interpret the ring buffer state, the receive ring buffer, and identify if there's new data to process, new data available from the network. I just saw this Twitch message, cbit 128 if only C had proper modern standard whip and sane string handling. Yes. that would make things easier. Okay. So the job here is to interpret the ring buffer state, and the ring buffer just for like memory is something like this. We have all these descriptors and stuff, and the hardware bumps in data into here and advances the head pointer, and then when it's time for our driver function to run, we observe this state and we observe that the head or the tail is over here, and then there's a couple of things that have been pushed into the queue, and it's our job to go through and like pop exactly one of them off and pass it on to user space, for example. So that's our job. So we basically advance, like look at tail +1. We check if there's a DD bit here, which means that the hardware put something there. And that's what we just see in the code right here. We get the tail, we look at the tail next. Actually, yeah. Yep, tail next one. And ignoring a few details, we just we check if the next one has the DD bit set. If it doesn't have the DD bit set, we return like this -2 number. Otherwise, we process the data in the descriptor. So it's time to we process the actual data which is sitting here, and then we point tail at here, and like can get rid of the DD bit, and that's what consuming one of these things looks like. So here we see the raw data. We mem copy it into the buffer provided to us, right? User space passes a buffer that we're supposed to write into. I actually just had a quick thing I wanted to check, and it is related, but I was looking through some other OSs. I'm looking at some other OSs that, so other people that finished this OS course. And I noticed one thing that I think I might be doing wrong, which is in my version of the code, I actually just declared my own variable for the receive buffer. So I need to pass in a buffer into the system call, which the kernel is going to write to. And I did it myself. I noticed in one other OS it didn't do this. I think it used this NSIPC buff thing, which already exists. Also interesting that it's, wait, I think I did the same thing actually though. Aligned page size, right? But actually, did I do it? No, I think I did. I think we confirmed this. I think I confirmed that this actually is aligning this onto a page size. So Sashin, how can I start with kernel programming? Is there any video that's available free by beginners? So I don't have any tutorials because so many other people have made tutorials. And honestly, I'm not even the best person to be making tutorials for this topic. But Nanobyte has some really good tutorials. I don't know. Lots of other people have tutorials on this, so you could watch some of those videos. Yeah. Empathy, I like your C coding style, that's what I use too. Cool, nice. Yeah, I'm kind of being kind of random with my coding style. I'm not being too rigorous with it yet. So anyway, there's this like existing thing which is here. It sort of makes me think I'm doing something wrong where I have my where I have my weird random global variable. So I think I should check out how people are using this NSIPC thing. So for example, in the output, here's how the output server works. They declared this union. But actually I never used it, but maybe that's a hint that I should have used it. I think that's actually a key hint. Also, is it? Where is this? Oh shit. Oh, okay. There's just, it's not in a header because it's just directly the extern thing is just declared here. How is this used? okay, wait a sec. There's this kind of pattern. The false root, yeah, it could be. Yeah. Okay, yeah, maybe, okay, maybe that is a bit of a false idea. So right into the console, that happens through this, through a console driver. It's pretty simple, I think. Put char, C put char. Ooh, no. Yeah, how does that work? So C put char is right here. So cons put char. It funnels down all the way into here, where it actually calls a couple of different things. I am not that familiar with it, but mainly we're using serial put C, which just contains this basic driver for some serial device. I didn't write this code actually, so I don't really have a good understanding of how it works. But does that help your idea of what's going on? Very interesting that, yeah, so we really did receive it here. And reset the descriptor, possibly not needed. Let me open up manual one time. Okay, this is hard to navigate. Where I'm looking for the receive. If the write happens all at once instead of character by character, there is a mechanism in ASIC to write a buffer. Okay, I don't know if I exactly understand that comment. What I'm kind of thinking of, I'm just double checking this structure declaration from the hardware. And I was just wondering if there's anything I need to zero out when processing the packet, but I don't really think so, because all of this stuff, the shaded areas indicate fields that are modified by a hardware upon packet reception. So hardware is going to write through all of this. So I don't really think it's important to zero things out. I do it kind of here. Then we advance the tail and we set the tail to the tail next value, which is just what we computed earlier, very simply. All right, quick 20-second break, be right back. I'm sort of wondering about the state of the head and tail through all of this. I'm a little bit curious about that. Add this. I'm just gonna print that out also. Head. Maybe there is something weird where the head or tail is getting incremented in kind of a strange way. That is the idea. I'm gonna copy test t like fail 100 one. Okay. So I'm gonna run this again. That is compiling a lot of stuff. Okay. Waiting for packets. Time to send packets. Boom. They all showed up. Okay. Kill this. Let's briefly scroll around. It happened very early this time at 32. At least that's good that it happens pretty early. And what do we observe? We observe the two 32s, which is the bug, and then we observe (31) and 32. Head is 101, tail is 0. I see. So here, tentatively, here's what happened. It's actually very interesting. I'm just gonna, oh wait, Michal. If the mechanism is used and the end of transmission is not checked properly and your buffer is reused, you can have a race where you overwrote what is outputted to the console. There's a mechanism in x86 to write a buffer. I'll keep that in mind. This is interesting though. I actually think this is correct, what we're seeing here. But it's I'm just going to screenshot this because it's interesting. I wasn't actually expecting the head to be that high. But it actually does make sense. So originally we were seeing, that head is 1 and tail is 127, and that's good. That's the initial state. It's like roughly the initial state we expect. Actually, head is initialized to 0. So here, what that means is that something was written into descriptor number 1. And tail is pointing at the last one, which is where it should be. And then it's actually and so after this process thing is done, tail at the end of this call, tail gets moved to number 0, and that's where it sits. And then here's what happened. Then on the next receive call, we see that head is 101 and tail is 0. What this means is that like all of those UDP packets in this script, they like arrived in an instant and the NIC just filled up, like the NIC really just filled up 100 descriptors in one go, which is actually good because that that also kind of simplifies things, as opposed to, as opposed to something where like the packets are kind of coming in as we're like popping them off, something like that. This is a bit more of a simple situation. The NIC just pushed like 100 packets into the buffer, and then now now the driver's waking up, and tail is still at 0, which is where it was at the end of the first call, and now it's time to like pop a single buffer off. And that's basically what happens here. Head, it seems like head just stays at 101 for forever, basically, because no new packets are coming in. Yeah, head literally stays at 101. It's actually kind of interesting that tail stopped at 99. Okay, I would kind of expect tail to be 100 actually, but I think that's a little bit less important. Actually don't know how to clear my search, but it's just interesting to observe this. So we can see, so basically just every time we call this function, we pop off basically just one thing. And we can just see tail start to increment, and we print out what we're processing. So we are processing the first one, 30, 30, 30, and that just appears here. I'm actually kind of wondering why the output is interleaved, actually. Because why is the output interleaved? Because we have a user space process that does a blocking system call. Like the driver and the user space process never actually run concurrently. The like user space, or is that actually true? No, actually no. I think that's not true. It would be true if the printing was happening here. So this is the process that's calling the system call. But the part that makes it like somewhat concurrent is that the printing actually happens in another process, which is triggered by our IPC message. So it would actually be very interesting to place interleave points to your idea of the rate of like this mechanism thing and the buffer reuse thing. Okay. What's up, Jafar, Sheriff? We are debugging an issue with my networking in the operating system. We have a problem receiving data. We are dropping packets and also duplicating a packet sometimes. We're trying to figure out why. Could be interleaving points to your idea. So, okay, maybe. I think I can understand the interleaving now. It's just because of this. It sends it to a different process. It's like roughly synchronous though. Like you can see the 30 here, then the 30 here, then the 31. But that actually gets skipped. That actually gets skipped. So so the driver sees a 31, copies it into the buffer. Oh. Wait a sec. Okay, maybe what's up, Johnny's shins? Are you working on an existing kernel? Kind of. Yeah, I'm working on this coursework. It's like this MIT operating systems class coursework, and so they provided a skeleton OS. Yeah, I think yeah, Michael, I think you're right. I think you're right. Let's the buffer gets overwritten. Let's sketch this out. This is interesting. So we have the parent process that does hex dumping. We have the input helper process that does the syscall, and we have the kernel driver. So these are conceptually like three sort of concurrent processes, except not really, because the kernel driver happens synchronously. But I'm just going to have its own lane just because. Can I make these longer? Okay, so here's the order of events that causes all the problems. So, so the first event is that this thing does a syscall to receive some data. AsmCube, unfortunately, not really. I think Miro allows you to have one free board, but there is a program called FigJam, which is free and basically the same thing, I think. So, I don't know. I haven't used it. I like Miro a lot. So this this receives pops one buffer off, writes it into the global buffer. And the key concept here is that there's one single global buffer, right? And so this thing writes it into the global buffer, and this thing blocks, right? So this thing, this process blocks while it does the kernel call. The kernel writes it back into the global buffer. And then this thing returns. So Mohammed, we're just doing kernel hacking here. Means kernel development and kind of tinkering with kernels. So now the input process returns, and it sends an IPC message with the buffer adder to the parent. And then the parent wakes up, hex dumps the global buffer. And I don't remember if this. Yeah, is it? Wait. Is this blocking? That's the question. It seems like it would seem as if it's not blocking. And it's not blocking. And the reason that it seems like it's not blocking is because we have this bug. If this was a blocking call, so the data gets filled in here, if this was a blocking call, then the parent can just safely wake up, read out the global buffer, and print it out, and then transfer control back to the helper process. But let me explain the bug. So here's the bug, and Michal also recognized this. So what could happen? So the input helper process calls the kernel, which populates the buffer and then returns. This thing sends an IPC message, and let's say this IPC message was not blocking, which means these two things are running concurrently. right? And then I'm going to get rid of these arrows which indicate blocking. So it sends an IPC message, but then it keeps going. And let's say it took a long time for this thing to wake up. Let's say it sends the IPC message, but then it doesn't block, it just keeps going, and then does another syscall, which triggers the kernel, which actually goes back and overwrites the data. And so we received one packet of data, and before the parent had a chance to look at it and read it out, we actually kind of like jumped in the way, did another read, and overwrote the data. And so by the time the parent process gets around to it, it's reading the second packet actually. And something like that is happening. And then the parent like reads it twice or something like this. So just to summarize the problem, there is a single global buffer for the data, and the parent seems to be racing against the input process. The parent somehow slows down, and before the parent can hex dump the data, the child goes and overwrites the data with a new packet, something like this. AsmQB, yes, we are doing networking. We have a very interesting bug in the kernel driver for the network card that we have literally just figured out the reason for, and we're fixing that. And the bug is just like we're dropping a packet and then duplicating packets and stuff like this. It's not good. Technically, this is all UDP though, and UDP is supposed to be a lossy protocol where packets are allowed to get dropped and whatever. But that's not really an excuse to have a buggy kernel driver. So yeah, we kind of have this problem where the input helper process, the child, can kind of race. It seems like it's racing against the parent. So what do we do? Can we make the child block while the parent IPC is running? Can we confirm that it's actually non-blocking? I actually was really unsure about this. I kind of thought that these IPC messages were blocking calls actually. So that's a key thing to do. And yeah, I don't know. I think how else would we solve this? Like maybe I don't know, do we need some kind of like lock or something? But that's kind of tricky because these are different processes. Yeah, Michael, yeah, technically the driver seems correct. So I agree. So it looked like there was a bug in the driver. It actually seems like the driver does not have the bug. The bug is like in all of the callers and just how they're coordinating things. It's basically kind of like a race condition. So let me get to these questions. So asking people, why not TCP? Yeah, I mean, that like so many reasons. Like, so we don't even have TCP at all right now. TCP is way more complicated than UDP. And since I'm just like barely getting like my network driver going, UDP is really the plain simplest way to get started, because it's a stateless protocol, and so you can just send packets, and there's no connection to establish. You just send off packets. So it's by far the easiest way to get started, just with like testing this and stuff. And what night? Yep. What kernel are you messing with? Yeah, it's this kernel from this MIT operating systems course that I'm following. So I didn't write a lot of it. I mean, but I did write a bunch of it at this point. What about atomics? Yeah, I mean, this is a little bit at a... this is a bit at a higher level. We would use atomics to maybe build a lock or something like that these two would use. But the problem is like a bit just in terms of how these two processes share concurrency. So yeah. All right, let's do the first thing here. Let's confirm this blocking or non-blocking thing, because we can do that fairly easily. So let's check that out. It kind of makes sense why the loop stabilizes things. Maybe. If this thing is running super fast, it's more likely that it's going to like win the race against the parent. Or is that true? I don't know. Because it's going to just like call it right here. Anyway, let's check out IPC send. I kind of forget how this works. So in this operating system, we have this IPC infrastructure where user space processes can send data to each other, but it's very simple. Okay, and then so here's the user space library portion, and what a process does is it calls IPC send and passes the ID of another process on the system, and all it really does is it just it just calls the system call try send, and then it yields every time actually, which is interesting. Let's look into the sys try send. So here's the implementation on the kernel side. And wow. Basically, what are we searching for? We're trying to see, does this call block? I think it does not. Like, we actually don't really need to understand this code to answer that question. Blocking would basically mean the current process gets descheduled and marked unrunnable, and so then it just stops running basically. What we see here is we just don't see that happening. We can pretty clearly just see that this function always gets all the way through. What we do is we have a target environment that we're sending IPC a message to, and we actually mark it runnable. So we put it into a runnable state. Yeah, we put it into a runnable state. And then we just return. And then we return like back into this thing. And we just do basic error check. And then we just yield. We just yield and loop and we keep just retrying the send until it succeeds, basically, actually. So, so input is what we wanted. So that's what happens here. So this, basically the short answer, this does not block. Well, it blocks in the sense that, okay, let me correct that actually. It like kind of blocks here. So if the target that we're trying to send stuff to, if there was some kind of error that didn't cause a panic, like, okay, what are the possible errors? So there's all these different ways it can fail. Okay, but there's this one specific one. If it's not received, if the environment is not currently blocked and waiting, then this is going to fail with a very specific return code. Yo, what's up, useless? Too cool. Definitely not. Definitely not. I would. Yeah, no. Definitely just trying out some new stuff. I just picked these up at a flea market. I thought they were pretty cool. Okay, so we can attempt to launch an IPC message at another process. If it was not listening for one, then we don't. All we just do is we return with an error, and that gets like a pass. And so if this thing was not 0 or not that specific error, we panic. But if it was not ready to receive, then we just loop and try again. Or if it succeeded, we actually just we yield. Yeah. So it kind of. But this is interesting. So let's say it worked. Let's say the parent process was sitting there ready and waiting, which I think it kind of should be. So here's how that works. We fork kind of high up here actually. We fork the input process, and it kind of just like immediately starts trying to receive stuff and pass things to the parent actually. So there could be an amount of time where this thing starts, it goes and gets a packet, and let's say that succeeded, and we come down here and it's like hitting send, but the parent is kind of still making its way down here. It hasn't hit the receive yet, and so it's still kind of making its way down here. In that case, this process is just going to kind of like spin. It's not able to actually do the send. But as soon as this thing gets here and gets into a receiving ready state, then this thing will be released, and it's going to come here and do another another system call and potentially overwrite the data. And so there is like sort of like a race here, because so this thing could be sending, and when it succeeds, it's gonna come back and start the loop over. And then let's say it succeeded. So this thing was kind of trying to come down and execute the hex dump. But this, fundamentally, this whole thing, like this actual data, this packet JP data thing, this packet, actually, what is that? That is, right, that's the way this process accesses the data exchanged between the two processes. And just fundamentally, it's like shared between the two. So yeah, and it's just shared. It's like shared data, and the other process can kind of overwrite it. Like in between here and here, the other process can kind of go through and overwrite the data and cause like a skip. Yeah, thanks for the tip, AsmCube. Yeah, we were using Wireshark a little bit earlier. The problem isn't really, like, the problem is purely in the way the OS is handling the input data from the network. So the Wireshark looked fine. So how do we fix this? So maybe just back to here to answer the questions. Okay, so what was the conclusion? It's kind of non-blocking. It will block, loop, retry if the parent isn't listening, but as soon as the parent can accept the message, we continue after the send. Yeah, okay. So I have one idea. So we can insert yields, actually. Technically there already should have been a yield here, but somehow there is this, somehow the problem is that this process is just not getting like enough time, weirdly. There is a yield built into IPC sandwich, so it's so when we do this and we trigger to send, this system call actively deschedules this process and gives the opportunity to another process to run. And hopefully that would give the chance for this process to kind of pick up here and execute the hex dump like undisturbed. But it seems like that's not really the case. Somehow there's like a way that it's like not getting a chance to run in a timely fashion. I could add a bunch of I could add like a shit ton of more yields here. Yeah, I don't know. I could add like a shit ton of yields here. I could also add a yield here. Maybe that would even be a better way than doing my weird loop. Okay, back to, sorry. The race is the access to, yeah, right. IPC already yields, exactly. Wait, the race is access to the packet pointer. But, so there, like, there's only a single core here. So just to clarify about that part, it's like not true concurrency, but so these, like, this process, the input, and the parent, they run in an exclusive fashion, kind of, from the CPU perspective. Have an intermediate recounted packet structure. Okay, Osloy. Maybe kernel should make a copy of the data in the global buffer instead of returning the global data address. Would that be too expensive? Okay. I mean, yeah, in general, more copying could be a solution here. Instead of returning the global data address, would that be too expensive? I mean, well, in general, we are actually doing a lot of copying. The kernel copies it from like the raw NIC buffer into this user space buffer. I think the problem is there's just no synchronization here. I'm also just clarifying and trying to remember a bit of these details. So the way the IPC works is we're kind of sending a bit of like a page of shared memory to the receiver. Yeah. And in one process we can construct like some memory and then pass that off, and then the receiver is responsible for declaring a place to receive that on their side. I want to just look at syscall again just to see the receive. Sys IPC. Something's kind of whack here. Why is it block until the value is ready? Record that you want to receive. So what does this do? Oh, we have some output parameters, right? So that's an output parameter. Okay, it's like kind of hard to understand because we have all these output parameters. But the input parameter is like this pointer. And that's just the thing we pass into the system call. Okay. And just what do we do with this again? We validate it. We store the address and then we mark ourselves as unrunnable. Okay, then the other side of this. Who is using this dest VA thing? Here's, okay, yeah. Here, specifically here. We, insert a page into their address space using the variable that they kind of registered with the kernel. Okay, so that was like a brief refresh on how the IPC mechanism works. I think we're close. I mean, Michael, you seem to be maybe even one step ahead of me. The race is the access to the packet pointer. Like, I definitely understand the general concept here of like, okay, this thing is kind of running and it somehow managed to like call the system call, overwrite the data. I feel like if these were threads, you could just use a mutex to guard this thing. Like this thing would need to lock the mutex before it tries to write to this buffer, and then it releases the mutex after. And then on this side, you would grab the mutex like somewhere like after here, like around here, for example, while you're actually using the data. But that actually doesn't really help necessarily, because if you grab the mutex here, there's still this window after the receive, maybe, where we could receive. Something could happen where we get like descheduled and the other one runs again and overwrites it. Like it gets the mutex here, writes it, releases it, and then we just are in the same situation. A dirty solution would be to use a spin lock. I think I'm still like, I still see this challenge even with a spin lock. There's like this race. Okay. How do we solve this? How do we solve this? We need to prevent this thing from calling this until this thing has like fully processed things. It is mysterious why this yield is not enough. That is a bit of a mystery. So like I mentioned, as a kind of a bad hack, that's not great. We could literally just add a bunch of yields. That's the simplest thing I can think to do right now. It's a bad solution, but basically this should hopefully really try to ensure that the parent process gets the time it needs to really make it all the way to at least here. The driver would block, and the main thread would unlock after the hex dump. Oh, interesting. So okay, interesting. So this call would block. I think it would be a bit like a condition variable, maybe. Like the condition variable would wait here, and then you would signal it here, and then it would wake it up maybe. I'll just write that down. Condition, add a condition variable somehow, make the input process and wait until signaled from the parent that the hex dump is finished. Or add many yields to try to ensure that the parent gets the runtime it needs. So my theory, yeah, I don't have a great theory here. There's other processes running on the system. There's not that many of them, but the other process that's running on the system is the file system server. Yeah. Okay, so actually what processes are running? There's the file system server. There is the test input process. And then there's these two child processes, the output and the input. And I think they are even literally there in that order in like the list of like processes. And the scheduler is super simple and just like, I don't know, how does it work again? Just like iterates. It's like, I don't remember, but I thought it was just like a very simple kind of round robin kind of scheduler, which just goes through each one. But so I have an idea. This is like pretty bad, but if we know that there are 4 and only 4 processes on the system, if we can maybe like kind of guarantee that the parent will get to run if we have like basically more than 4 yields. So we can think of this process as being like super fast and like trying to overwrite stuff, and these yields like really slow it down. And each of these yields is going to give some process an opportunity to run. We don't know which one. And in the worst case, it gives like it allows all the other processes to run except the parent, which is what we really need to run. But if we have like 4 yields, I think everyone will get a chance to run at least once. And hopefully the parent only needs 1 time to run to get to the hex dump. So, and then here I have like 8 yields or whatever. So that should be like way more than enough. Which will definitely slow down receiving data in the OS, but I am kind of hoping this will work. So with this in place, I think we can just run the test again. Like we can just run the grading script again, grade. So this is 100 packets, grade lab 6. Let's just see if it works. It worked once. Yeah, if no other processes are ready, yield should return immediately. Let's check. It worked twice. Let's check let's check scheduled. All right, let's actually start from the system call. Sys yield. All that sys yield does is called scheduled. Scheduled takes no arguments. Right. What? Especially ends for a runnable environment. Just after the env, this CPU was last running. So we find the one that was just running. No, that's literally the last one. Preven is the one that was just running. Then we have this like cursor, like set the state of the cursor somehow. In general, we're just setting it to like +1, the next one. We're looping in a loop of all the environments, and we're just seeing, based on the current cursor, are we runnable? And if we're runnable, we just execute it. Otherwise, we like advance through it and loop around this like ring buffer kind of thing. Okay. Phase 1 is like try all of them and execute one that we find. Phase 2 is okay. If none of them were runnable, we can drop back into the one that we actually were running, as long as it's still runnable. Otherwise, do a sched halt. So what would be kind of neat here is actually if this process can mark itself as not runnable, if this process can actually mark itself as not runnable, that would help guarantee this thing would just need some kind of system call to mark a process as runnable. So that's conceptually similar to this condition variable thing. So one implementation would be input process marks itself as unrunnable somehow. Then the test input parent can also use a syscall to mark it as runnable again when it's finished hex dumping. That might be interesting to try. I'm kind of curious. Remember, the CA doesn't want you to know about switch statements. Osley, how big is the global buffer? Is the global buffer a buffer just for packets? Are packets all the same size? The global buffer is 2K bytes, 2048 bytes, which is chosen because it is larger than the size of a maximum Ethernet frame. So it's designed to fit one Ethernet frame. And yes, it's a buffer just for packets. Packets are guaranteed to be no larger than this global buffer. But let's just see if this yield hack works. Like, it kind of actually seems like it's kind of working, which is not really that satisfying, because it's like such a hack. But it really does seem to be working. That is kind of the question, though. How can we be really sure of this? So just to come back. So here's the grading script that we're running, and we're running the 100 packet test. We can even do a stress test. Like, what if we did like 500 packets? Taking kind of a long time. It's complicated to prove the absence of something. Oh, whoa. Dang. Okay, so we added many yields to the input loop. That seemed to fix the 100 test. It didn't fail in a few times, but the 500 test failed. Damn. Wait a second, this is suspicious. It failed on packet 129. 128 is the size of the receive ring buffer. So that's kind of suspicious, actually. Let's run this one more time and see if it fails at that same spot. That would indicate that there is a problem with the wraparound of the ring buffer, which would be bad. It's also not really good that it's taking this. It failed at exactly the same spot. Here's what I'm going to do. I'm going to bring this back to 100, but I'm going to change the size of the receive ring buffer. Or should I? Yeah. It's at 128. What if I just make it like way smaller, like 16? Or even 8 or something. I'm actually curious if our tests still pass. Even the 50, does that still pass? Because that was kind of suggesting that the fact that this thing doesn't work, it suggests that there's a problem with the wraparound. Why is it so slow? Why is it so slow? Yeah. It's slow because it's timing out. Trying to kill 2 bugs with 1 stone. All right, this is interesting. This definitely means we have a problem with the wraparound. These numbers are way too exact. A problem with packet 17 and packet 129. And what seems to be happening is something blocks, and then the kernel just like hangs, and then it times out after 30 seconds. Can we debug this quickly? Well, before we jump into that, I just want to say I feel like we have discovered a new bug, and I think that sys yield hack actually did fix that first bug. So I think we can it's not a clean solution. It is kind of a bad solution. it actually really decreases the throughput of the receive side of the S, because this input process is so like restricted and it has to yield so much. But I think from just like a correctness point of view, it does work. Let's well, yeah, what do we do now? Let's run the OS. We don't need this thing anymore. And let's just reproduce this issue. I'm not going to do something crazy. I'm just going to do 25, and we still have our send script. So let's just see what the debug logs say, I suppose. No, also no problem, Osloy. So wait, I forgot to t it, test t2. All right, bam. Let's test t2. What's up, Icron? Yeah, summertime coding. What is going on? Why did it say head and tail are both 15? Oh. I think I know why. I think I know what the problem is, actually. So we were trying to send like a lot of data. We were trying to send actually more data, like a larger number of packets than what we have available in the descriptor ring buffer. And what we were seeing is that all the packets after like the end of like the ring buffer go missing. We see this in the 500 case, everything with a buffer size of 128 packets. From the 129th packet, they're all missing. And then from in the 16 case, they're missing from packet 17. But the reason for this actually is because I think all the rest, they just literally get dropped. So we were seeing before that it seems like all the packets just like arrive at once in the NIC buffer. And that's fine. But if the NIC like had even more data to write to than space was available in the buffer, the NIC is actually not going to wait around, I think, for the next time it's free. The NIC is just going to like drop packets. So I think that's what we're seeing here. Simply, and one of the reasons I believe this is you can see that we have head and tail are both equal to 15. And if we just go up to our diagram, this is a simplified example. Sorry, head is here, tail is here. This is a simplified example, but head and tail are both at the end. That means every single one of these things has been consumed. And the queue is like actually empty now. So I actually don't think it's a issue with the driver exactly. The driver, like, it was just simply just too much data in one burst, and we were not able to process it fast enough, something like this. So that's the explanation. So that's a bit of a separate topic. Okay. This seems like the additional data that doesn't fit in the RX buffer is simply dropped. Not necessarily a driver bug. Question: why? Yeah, I guess there's just like a problem, like the OS is just like kind of too slow or something to like, why can't the OS process the data as it's coming in? Like in real life, the NIC and the driver run concurrently, and as the NIC is pushing in new data, the driver is like kind of popping it off and stuff. It seemed like that this is not really how it works. I mean, in the emulated environment, a lot of things are different. So yeah, I don't know. Our throughput is super low somehow. Maybe that's we can't receive data fast enough. But it also seems like we didn't even try. But it seems like all the data is in there instantly. No chance to process it. Even on the first receive call. Something like over here. I mean, this is literally the first time the receive driver is even getting called, and the thing's already full. There was no opportunity to like do anything else. I kind of wonder what would happen if I just like waited a long time. Too much yield by forcing the output. The next try and fails to queue the message. Yeah. Okay, let's say I just ran the OS, okay? So the OS is like sitting there, it's waiting. The queue is not full because I haven't launched like the big like blast of packets yet. As soon as I run this script, the Python script is going to start going in a loop, sending data to the OS. And like I don't have any sleeps or anything here, so it's going to go pretty fast. But the OS, at this point in the OS, it's like actively waiting and polling, and it's actually ready to receive stuff. So I would kind of think that at this point, it should be ready to process some packets, and maybe even keep up. Also, a key thing that I kind of forgot is that we still have this crazy slow loop that is slowing down our receive. Maybe that impacts this. So I'm just gonna try to do the send, and let's just see what happens. All right, let's test 3. So this is different because this time I waited a long time before sending the big blast of packets. Actually, now that I think about it, in the last experiment, I just like blasted the packets even before the ARP thing went through. And so I just immediately overwhelmed it like really early. Lol, that loop. Yeah, so here, So now this is like kind of interesting. So definitely changed things, but we can also just see that like head and tail both got set to 0. Here's what that means. So back to our, so what that means is that it's still filled up instantly. So head is initialized here, tail is initialized here. The first thing that happens is this like ARP request and response during boot up, so that the response sends one packet here, and then we process it, and this points here. And so now tail points at 0. And then the next thing we see is that head and tail are equal, which means that head like got bounced all the way back over here. And so it just means that even still, like we received way too many packets at once. But actually, we definitely don't need this anymore. This is like stupid. We were using this because it helped stabilize like the race condition a little bit for debugging. But now that we have our fancy fix with all these yields, we don't need to slow down this process still, but it's still like really limited by this IPC. So kind of, now that I think about it, it doesn't really matter. In order to keep up with like the rate of traffic coming in, this thing needs to like go fast. So we can just do an experiment though, just out of curiosity to see what, I'm just gonna call this T4. I'll let this run. So now it's waiting. I'll blast the packets in, and I think that was kind of like the same thing. Or was it? No, it wasn't the same thing. Check it out. I mean, I don't know if the end... A race was fixed by forced yield. Oh, sorry, night. No worries about being ignorant, also. Why was it fixed yielding? Okay, then Michal was explaining. Problem not being there. Fixed by yielding. Maybe I'll just also try to explain it in addition to Michal. Like, the main reason that the yielding fixed things is the problem was that, so this code is running in one process, and then this code, which does the hex dump, is running in a different process, and it's critical that this hex dump sees and hex dumps every single packet. What was happening, for sort of mysterious reasons with the scheduler, is that we're like writing data in on this side, and for some reason the parent is just not getting the time it needs, and it was missing like a packet. Like, something was happening where this thing would like run too fast and actually overwrite the previous data, and that overwrite caused it to, like, this process to miss a packet basically. So by spamming the yields, we basically ensure that this parent process will get the time it needs to see every single packet basically, because we just like really slow down this one by a lot. But it's interesting that commenting this out, it actually did change something. I'll just take a screenshot of this. So let's just pay close attention to these head and tail pointers. So in the previous like situations after the initial ARP dance, the head and tail were always equal to each other. So this is the ARP dance. But this time, head and tail are not equal to each other. Actually, head is only 3. The buffer is like 16 long. And so what this means is that our receive process was able to react much more quickly to the new data that was coming in. Because with the old crazy loop here, it would try and then it would wait for like a long time. I don't know, like a second maybe. And even 1 second of waiting is long enough for the entire receive queue to like completely fill up. But without that loop, this thing is running super fast now. It's running like, I don't know. It's basically running as fast as you can do system calls. It's going super, super fast. It's kind of spamming the kernel with all these system calls, but that spamming is allowing it to react extremely fast to new packets. And actually, it's able to react super fast. And what this means is that head was at like 1 or something. And so now head's at 3. And so the NIC is pushing in 2 packets, but we're already there trying to receive it actually. So yeah, as fast as Sonic for sure. So I don't know if that, like in the end, I don't actually know if that helped with anything. Because so I don't like that helped us be there to receive, like, to not get completely overflowed right off the bat. But the problem still exists that we're like yielding like really hardcore here. And this much yielding might be enough to allow the NIC to overwhelm the buffer with data. And I guess to really figure out if it worked or not, we could like, what IPython like 3. I don't know if you can see this in the, okay, yeah. What is 14? Right, and so I think it did not actually help because we're trying to write 25 and all we got to was 14. So I think that did not actually, like, the problem is like the throughput basically. Our throughput like kind of sucks. And so we could maybe fix all of this with like those system calls I was talking about. So the idea is, well, the problem is also that like we're like kind of slowed down by this like UI process basically that's like trying to print stuff. And we can't buffer internally also, we're like just directly trying to send to them. Yeah, to be honest, I have actually no idea how like real OSs like managed to like process so fast, or maybe they just don't. I mean, it is kind of up to applications to be like high performance and like read data if it like be like reading data if they want to receive at like fast rates. Yeah, I don't know. But anyway, so the other solution that could possibly help here is instead of doing all these yields, we do some new imaginary system call. Like, it would basically be like yield. It'd be like sys like yield and sleep or something like this. Like, not only do we yield, but we like forcibly make our own like process unrunnable. And then in this process, we would have something like sys wake up, and then we can like pass, I don't know, the whom. There's this whom thing where we get to find out who is sending us messages, and this thing would like wake up that other process, maybe something like that. I'm missing chat messages. Another dirty solution could be to put the driver to sleep and waking it up after the dump, but the scheduler does not support sleep. Yeah, also the problem with putting the driver to sleep is that currently the kernel cannot like get preempted and then like woken back up, because there's like there's a single kernel stack, and that will get like trashed and like reused by anyone else that uses the kernel for anything. So if I understand correctly, I think, yeah, I think that's a problem. But yeah, I think this like kind of weird, this thing is basically a condition variable. This pair of system calls, for anyone that's not familiar with this, with a condition variable, it's not exactly a data structure, but it's like a synchronization primitive that's available in like libpthread and stuff. Like, there's mutexes and there's also condition variables, and condition variables are different because they implement signaling semantics. So one caller can like wait, and then some other caller can like signal the waiter to keep going. And that's kind of a different semantics than like mutexes, which are all about mutual exclusion. But with this signaling semantics, we can help. By sleep, I mean processes are running but cannot be suspended. Like a sleep state. Okay, so yeah. I guess, I mean, it does support unrunnable. Like, there is an unrunnable state, which to me, that's kind of like what I understand a sleeping state to be. Can we? Okay, I need to like go kind of soon, but I wonder if we can just like hack this quickly. So what's yield? What if I added like yield 2? Or just yield and sleep? And then what if I passed a 1 in here? And then I went to here, sys yield. And then instead of being void, I was like bool should sleep. Then it's like if should sleep, cur env status equals env non-runnable, for example. So that's just like super basic, like hacking this. And then that means any other callers need to be adapted. So I'm just going to call A1. That's the only caller. So now we sort of have our like new weird wait and sleep system call. And then now we need to add a system call for this like kind of strange wake up thing. Use a for loop instead of calling sysyield repeatedly. That should help. That could definitely help. So now we have our sys wake, which is sort of weird. Wake up, and this thing needs to take and okay, this thing needs to wake up. So now we have our sys wake up, and then this thing just needs, and I just need to like implement this wake up and env ID. So here's an example of a system call. It takes a process env ID. And what do I do with it? I need to I'm like really just kind of trying to go very fast here. Return ret or return 0, and then all we do. Okay, and I need to make a struct env and status equals runnable. Okay. This is like, maybe I'll just put the 0 in there. This is like some weird check thing. What else is necessary? So I have, so this thing needs to do sys wake up, and we need to pass an env ID t and then this thing, apparently you can like pass it in like this. So I have just tried my best to go super fast and add 2 system calls to the kernel. And so yield should, yeah, just yield and sleep. Does this compile? Implicit declaration. Oh, do I need to where are, is there some header files? Syscall.h lib. Oh yeah. Okay. Okay, does this compile? Okay, that compiles. Super hacker mode right now, so I needed to go to over here. So now we have our new fancy system call, sysyield and sleep, which like forcibly puts us to sleep. And the difference is that, like, just to really emphasize this, or the difference is that with scheduled will always, if it couldn't find anything else to run, it will still run your current process. Oh shit, if it's running. Okay, I don't know. It checks if it's currently running. It's like kind of weird. But anyway, that shouldn't matter, I guess, because we're just trying to disable this. We're just trying to really prevent any like this thing from running until it's explicitly like allowed to. And so we have our input, so that's what we're doing over here. And then on the test input.c, oh shit, I gotta go. We got sys wake up, whom, lib.h, do sys wake up env id t env id. Does this, and whom is like the env id, so I think that's valid, so we run this. That also compiled. And what do we do? What do we do now? So now we are using our fancy mode, and I'm just gonna go back to the grading script. So we have this. So I'll also reset our descriptor size back to like kind of a large number, just for basic testing. We can test that later maybe. So now we're at 128. So now I'm just gonna go through the basic tests here of like 100, let's say. Can we pass that? And that should pass. That would really suck if that didn't fuck. Okay, damn, man, that really sucks. I don't know what's going on. Missing packet 1, 2, 3. Something got kind of borked there. All right, y'all. I'm sorry, but I failed you. I was not able to speed code the 2 syscall condition variable solution in like a minute. This is not working, but maybe there's like some small thing that we can fix later. I need to leave. But I want to thank you for joining in. Thanks Osloy. Thanks Michal. I gotta go. I'm just gonna promote myself. Here's my Discord server if you feel like continuing the conversation. Have a great week. I'll see you all next week. Have a nice one. Bye.